Okay, here's question number 3 from our free response section. It's a 12-point question with a suggested time of 25 minutes. And it's about a disk that's rotating. And this is essentially a problem where we're considering um, angular motion, rotational motion, torque, inertia, and so on. So the disk is shown spinning about that center axle, and while the disk is spinning, friction between the axle and the disk exerts a constant torque on the disk. So right here, this axle rubs against the inside diameter of that disk, I guess, and it basically is slowing it down over time. Okay. We're told that at the beginning, t equals 0, the disk has an initial counterclockwise angular velocity omega 0, and it later comes to rest at a time t1. And we're asked to sketch a graph that could represent the disk's angular velocity as a function of time, and then the disk's acceleration as a function of time. So let's go down and take a look at the angular velocity graph, okay, which looks like this. Um, if here's omega 0 and here's 0, and this is a time t1, so you could draw a linear function that just connects omega 1 down to 0 at time t1. That would be our angular acceleration, okay? Um, why this shape? Well, if it's a constant torque, there must be a constant acceleration on the disk, and that means um, that the angular velocity must be linear. Slope of the angular velocity graph is angular acceleration, which is the same relationship that velocity and acceleration have in the translational world. So we go down to here and we pick some arbitrary location here for our angular velocity, and I've labeled it minus omega 0 over t1 because the change in y is negative omega 0, the change in x is t1, and so that would be our slope. All right. Might as well reveal the rest of the problem here. It says the magnitude of the frictional torque exerted on the disk is tau 0. Derive an equation for the rotational inertia I of the disk in terms of tau 0, omega 0, and t1, and physical constants as appropriate. So in general, we know that tau, the torque, is equal to the moment of inertia times the angular acceleration. This is the F equals ma version of rotational motion. We're told that tau exerts a frictional force. Tau 0 is the frictional force. It's the only force acting on this object. And we've already calculated that the angular acceleration is minus omega 0 over t1. So I've got tau 0, omega 0, and t1 in there, and all I need to do is solve for I. So a little bit of manipulation around here, and you'll get tau 0 times t1 over omega 0 with a minus sign in front is equal to the inertia I, and there we go. We're all set. I gave credit for answers that left off the minus sign, so that you might have benefited from that. Okay, let's take a look at the next question. All right, this is let's reveal just a little bit at a time here. Okay, so now we're told that halfway through that time, at 1/2 t1, a student starts dripping oil on the surface between the axle and the disk to reduce the friction. So on the grid on the left, we want to show now what the angular velocity would be. So let's start to reveal that. Okay, out to half the time, the problem doesn't change in any way at all. But with a little bit more time, you can see that we don't quite get down to zero. It's still spinning, and I'm trying to show a little bit of a curve here. A little tough to pull it off, but I'm trying to show a little bit of a curve of the angular velocity at that point. And I gave all kinds of credit for anyone who showed the same slope to the halfway point and then a little bit of diminishing out to T1. What that means is that during this time, during the first half T1 seconds, the angular acceleration is going to be exactly the same as it was before, but then the slope of this would be less and less negative, possibly even getting to zero. So any kind of a graph that showed an angular acceleration that was the same out to half T1 and then less and less negative um, over time would get credit from me. Okay, so those were 2 points each, and it's really thinking carefully about what you've read and how to interpret that. Less and less friction would mean that there'd be it would take longer and longer to get to zero velocity. Okay, last question here. I found this to be a little bit puzzling at first. There's two possible answers here given to describe the torque. The torque would be constant during this time, but of course then the torque would be changing during that time, and the torque should decrease. Okay, so you're asked to choose one of these two expressions as a possible way to mathematically model the torque in this time frame between half T1 and T1. And in each case, you got these constants C1 and C2 that would be chosen just right. The torque would then depend upon that constant, either multiplied by a term or divided by a term. And what I like about number one is that it doesn't do anything to the torque when when t is equal to half T1. So right at this point here, that would turn out to be zero. And there's something appealing to me about that, but that would actually imply that the torque would be zero at that point. So that's not good, and for another reason, it's not good. As t increases, this parentheses increases. We're told that C1 is positive, so that keeps increasing. So the torque would keep increasing with increasing time in expression number one. We know that the torque must be decreasing, and so if we look at number two, even though I don't really like this denominator as t plus 1/2 T1, but nevertheless, as t increases, the denominator increases, the entire expression decreases, and torque would decrease as time increased. So I chose expression number two with the explanation that the torque must increase, and in expression number one, the torque increases. Expression number two, the torque decreases. So that's our response to question number 3.